Hello everybody, welcome to AP Chemistry Day 33. Obviously this is a virtual lesson for you to do over MEA this year. And so hopefully you'll get a chance to do this sometime between Wednesday and Monday night, because we have Mold Day on Monday. Did you hear about the big circus fire over the weekend? Yep, it was intense. Quick look ahead at the next couple weeks here. First of all, just a reminder to get your AP registrations taken care of. Since you're at home doing this, you could walk downstairs right now and say, yo, peoples, help me get my AP registration taken care of. After a look ahead, Monday obviously will be our Mold Day celebration. Tuesday and Wednesday we'll be doing POGL on polar versus non-polar, as well as some notes. Thursday, we'll be doing hybrid orbitals and some molecular orbital theory. Friday, you'll get a problem set and some infrared spectroscopy. The following week, Monday, will be your practice exam, and then a week from Tuesday will be your exam. The learning targets for this unit are for us to finish up talking about covalent bonding, and as well as bond distances and bond energy, and then for us to start talking about VESPER, and using VESPER to predict molecular geometry, bond angles, and bond energies. In theory, we should have had all of the properties of covalent bonds POGL done or very nearly done by the time you left school on Wednesday. But if there are any questions, send them my way. Same thing, if there are any questions on the notes for bond enthalpies and covalent bond strength, please send those my way as well. All right, so left side for the bond enthalpy and covalent bonding notes. A couple different things here, right? First one, rank N2, P2, and AS2 from weakest bond to strongest bond. Justify your ranking. And then below there's a bunch of true, falses, and why. Take a moment here, stop, go ahead and do those on the notes, and come back here when you're done. Okay, so hopefully by looking at these, you recognize that these are all going to be triple bonded substances. They're all in the same group on the periodic table. And so as a result of that, N2, P2, and AS2 are all going to be triple bonded. So bond order is not going to matter very much here. But what will matter is the distance the molecules can be from one another. And so N is the smallest radius atom, P is next, and AS is the farthest. So following Coulomb's law, weakest is going to be AS2 because they're furthest away from each other, distance is greatest, then P2, and then the strongest bond is going to be N2 because they're the smallest, and so therefore by Coulomb's law, they'll have the strongest force. All right, how about the rest of these? True, false, why? The bonds in NH3 are shorter than the bonds in NF3. Okay, so again, this is going to be based on size. So H is a smaller radius than F, so NH3 will be shorter than NF3. Okay, so this one is true. Second one, the bonds in NH3 are weaker than the bonds in NF3. Longer bonds tend to be weaker, so that would mean that NH3 is actually stronger bonds than Na4, so that one would be false. Bonds in CCl4 are shorter than the bonds in CBr4. Okay, so again, Br is below Cl on the table, so that means Br is going to be larger, right? And so CCl is going to be shorter. Okay, so this one is true. The bonds in CCl4 are stronger than the bonds in CBr4. Okay, so again, shorter bonds are stronger bonds, so that one is also going to be true. All right, and last but not least, the CN bond in H3CN H2 is easier to break than the CN bond in HCN. Okay, so a couple things here. Drawing out Lewis structures real quick. There's HCN, H3C, and H2 looks like this. Okay. And so again, CN bond here is going to be a single bond. CN here is going to be a triple bond. By bond order, this one will be stronger. This one's weaker. So this one would be easier to break. And so that one is also true. Okay. In Schoology, you will find a 3-point assessment for this. Again, that helps me know what you know. Go ahead and do that. And this one you're actually going to submit to Schoology. Okay, so you're going to do it on Notability and submit that one to Schoology. In Schoology, you will find a set of notes about VSEPR theory. You're always welcome to take your own notes as well. At the end of the set of notes, please date and topic, or please do summary and questions, and submit that. All right, so electron pairs, whether they are bonding or non-bonding, repel each other. So the pairs of electrons repel each other. What do I mean by pairs of electrons? Well, imagine that we've got a simple methane molecule. What they're talking about is this pair of electrons repels that pair of electrons, repels that pair of electrons, repels that pair of electrons. All right. So when that happens, those electron pairs are going to get as far away from each other as possible. And when that happens, you get an inherent shape of a molecule. You can get linear geometries, which have a bond angle of 180. You can get trigonal planar geometries, which have a bond angle of 120. You can get tetrahedral geometries, which have a bond angle of 109.5. And a couple others here, trigonal bipyramidal, where you have 90-degree angles on the top and 120 around the midsection. And also octahedral, where everything is 90 degrees to each other. Okay, so that's all. Some of these deal with expanded octets. Others of these deal with other exceptions or multiple bonds. All right, so the shape of a molecule plays an important role in its reactivity. How molecules bump into each other, how frequently they can bump into each other in the right arrangements to make rates happen, makes a molecule more reactive or less reactive. What determines the shape of a molecule is always going to be the bonding and non-bonding electron pairs that we have. And so if we note those, we can easily predict the shape of a molecule. Is it linear? Is it bent? Is it trigonal planar? Is it trigonal pyramidal? Is it T-shaped? Note on pronunciation. Mr. Murray says this word trigonal. Mrs. Lee, for those of you who had her, says trigonal. Potato, potato. So this idea that we just summarized is called the valence shell electron pair repulsion theory, or VSEPR, right? So valence electrons are what we're talking about. Those are the ones involved in bonding. The electron pairs do what? They repel each other. Okay, so the best arrangement of a given number of electron domains is the one that minimizes the repulsions among them. Okay, so an electron domain is a bond or a pair of unshared electrons. So that would be a domain, that would be a domain, that would be a domain, or that would be a domain. Okay, so in terms of multiple bonds, it doesn't matter what kind of bond it is, a single, a double, or a triple. This is all one domain, just as this is as well. Okay, all right. So in your textbook, Table 9.1 contains the electron domain geometries for 2 through 6 electron domains around a central atom. Also in Schoology, I have posted what I call the handy helper. The handy helper helps us get through these geometries quite quickly and figure out what we've got going on. So here is what the handy helper looks like. Okay, so when we talk about electronic domains, on the handy helper, they refer to that as steric number. So those things are the same thing. So again, if you want to write this out, you can just say domains, right? And that is just simply the number of directions bonding and non-bonding electrons go around the central atom. So again, as I think about it, if I go CH4 like that, how many domains do I have? I have 1, 2, 3, 4 domains. Okay. Likewise, if I did something like this, how many domains do I have now? We look to our central atom and we look around it. 1, 2, 3 domains around it. Okay, so again, that double bond there just counts as a single domain. I could also do something like ammonia. Okay, how many domains? Around that central atom, 1, 2, 3, and the bonding pair is 4. Okay, so that's going to all give you the number of domains. So that's what we go this way with. This one here, then we combine that domains with the number of lone pairs around the central atom. So this would have 0 lone pairs around the central atom. This likewise would have 0 pairs around the central atom. Yes, there are lone pairs out here, but those aren't around the central atom. Here we would have 1 lone pair around the central atom. Okay, so if we get that then, if we get our number of domains and we get our lone pairs, that gives us our overall shape. Okay, in general, it is important for you to know particular shapes. Certainly the ones in this first row are super important. Linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. A couple others that are important. Bent is always important. Seesaw and T-shaped are always important for us to know. So those are the ones that are probably the most important things for us to understand. But more so, you don't even necessarily need to know that if you can visualize this stuff in your head. But you need to get to a point where you can go ahead and you can identify what shape a molecule is from the electrons that are involved in it. I will be posting a Quizlet that has these different combinations so that you can start working on knowing those. All right, so having non-bonding pairs, there are a few ways that we can alter the standard bond angles for various geometries. So again, if I have a linear geometry, the standard angle is going to be 180. If I have a trigonal geometry, the standard angle is going to be 120. If I have a tetrahedral geometry, the standard angles are going to be 109.5. Okay, and again, as I said, sometimes you need to know the 90-degree angle ones as well that happen in trigonal bipyramidal or octahedral. Okay, but as long as you know that those are the standard, these standard bond angles are ones that you're going to need to understand. Okay, now if a molecule has a non-bonding pair, okay, those non-bonding pairs are physically larger than bonding pairs. They take up more space. All right, so as a result, their repulsions are greater and they tend to decrease the bond angles in a molecule. So here we have a standard tetrahedral, which has 109.5. If I move to ammonia, we've got a lone pair up here on the top. What is the effect of that? Well, it takes up more space, so it does more repelling down in this direction. So that means these angles up here on the top are going to be a little bit greater than 109.5, whereas the ones down here on the bottom are going to be a little bit less, and in this case it's 107. You would never need to know that exact number. You would just say a little less than 109.5. Okay, if we add even more lone pairs of electrons, like in water, again, this angle is going to get bigger. These angles are going to get bigger, but this angle between the O and H, that's going to get squished down to 104.5. Again, because these lone pairs are pushing down on the angle. So in addition to knowing that lone pairs will do that, the other thing that you should know is that double and triple bonds also do the same thing. They create greater electron density on one side of the central atom, and so therefore they are also going to do more repelling. Okay, so in a molecule like this, where our standard geometry would be trigonal planar, these angles closest to this double bond would get a little bit bigger than 120 degrees, and the angle down here between the chlorines would become a little less than 120 degrees. And that's indeed what we see when we measure those bond angles. When we get to larger organic molecules or larger molecules, it makes more sense to talk about the geometry about a particular atom than the geometry of a whole. So we would never ask you, what is the shape of this molecule? What we might ask you is, what is the molecular geometry around this carbon atom? In that particular case, you would go, oh, I've got 1 domain, 2 domains, 3 domains. Around that carbon atom, it would be trigonal planar. Or I could ask you around this carbon atom, and you would say, oh, I've got 1, 2, 3, 4 domains. Oh, around that carbon atom, it's tetrahedral. What is the... So that brings us to our left side for this particular set of slides, notes. So if you could please go ahead, on your left side, go ahead and sketch out the glycine molecule below. This is an amino acid, one of the essential amino acids that is used in our bodies and in living things to create proteins. What I'd like you to do is I'd like you to take the 4 atoms that are pointed to by the arrows, and I would like you to, for each arrow, tell me how many electronic domains are around that atom. What is the electronic geometry around that atom? What is the VSEPR shape around that atom? And predicting the bond angles. Now, sometimes people wonder, what's the difference between electronic geometry and the VSEPR shape? So electronic geometry is just saying, oh, it's got 4 domains, it's tetrahedral. Okay. VSEPR shape takes into account, of those 4 domains, how many are bonds and how many are lone pairs. So I could have a molecule that would be tetrahedral if they were all bonds, but I could also have tetrahedral electronic geometry, but a trigonal pyramidal if one of them was a lone pair. Okay. So again, go ahead and for each one, 4 things: number of electronic domains, electronic geometry, VSEPR shape, bond angles. Okay. We'll come back in a moment after you've done that all. Okay, let's get started. We'll start with this nitrogen that's right here. First of all, how many domains are around it? Well, I've got 1, 2, 3 bonds and a lone pair, so that's 4 electronic domains. Okay, what's the geometry? Well, when I have 4 electronic domains, the electronic geometry is tetrahedral. Okay. What is the VSEPR shape? So again, I've got 4 electronic domains, but one of them is a lone pair of electrons. That VSEPR shape is trigonal pyramidal. And last but not least, what is the bond angles around the atom? Okay, so typically a tetrahedral would be at 109.5 degrees. We've got a lone pair of electrons, so these angles down here on the bottom, those are going to be a little less than 109.5 degrees. And the angles between the nitrogen and the hydrogen on the top are going to be a little bit more than 109.5 degrees. Next, let's do this carbon. Okay. Again, how many electronic domains? 1, 2, 3, 4 bonds. So 4 electronic domains. Okay. What is the geometry? Electronic geometry is tetrahedral. Okay. The VSEPR shape. Okay. So 4 domains, no lone pairs, is also tetrahedral. And since everything is tetrahedral and I don't have any multiple bonds or lone pairs, that means that my bond angle is going to be 109.5. Okay. Ish, approximately. Okay. Next, we're going to go ahead and we are going to say, what about the next carbon around? Okay. So this carbon has 1, 2, and a double bond for 3 electronic domains. Okay. The geometry for that is trigonal planar. They're all regular bonded domains, so there aren't any lone pairs. So that means that the VSEPR shape is also trigonal planar. And last but not least, the bond angle. Bond angles should be approximately 120 degrees. Okay. Last but not least is this oxygen right here. Okay. So it has 1, 2, 3, 4 domains. That means that its electronic geometry is tetrahedral. Its shape, okay, so 4 electronic domains, but 2 of them are lone pairs. That is going to be a bent shape. And last but not least, what are the bond angles? Okay, so the bond angles between the carbon and the hydrogen on the bottom there, that's going to be less than 109.5. These bond angles on the tops between the lone pairs and the bonds, those are going to be greater than 109.5. Hopefully that all makes sense to you, because, all right, so then that brings us to your assignments. Okay, so again, you should add your summary and questions to the bond enthalpy notes. You should add summary and questions to the VSEPR theory notes that we just went through. Okay, and last but not least, you're going to go ahead and do problem set 4E. All that will be due Monday night for Tuesday. Have a good rest of your weekend.